Hey everybody, so we're going to take a look in this video at exponential and logarithmic integrals, as you might have guessed. So what we're going to do in this, we're developing some rules for taking integrals. There's going to be different techniques that we develop throughout these videos. The technique right here is just remembering some derivatives, right? Because recall that when we write something like, let me make that a little smaller. When we write something like the this integral symbol, we're looking for the antiderivative, right? So if I tell you that this is equal to some function plus a constant, what I can say equivalently is that this means that the derivative of the thing I came up with is equal to the integrand, the function we started with, right? And so if we happen to know this relationship, it gives us this one, right? Like we should really have arrows in both directions. Either one of these implies the other one. So we're going to leverage some derivative rules we know to create some antiderivative rules, okay? So the two we're going to look at first are, we know that if we take the derivative of the exponential, we just get the exponential back. So what I can translate this into a rule about antiderivatives by saying that the antiderivative of the exponential is just the exponential itself, except we pick up this constant of integration, right? So it's not a perfect relationship because of these constants that show up, but we get the family of functions from our derivative rule. And we can generalize this a little bit more. If we have a base for the exponential that's not e, then we get the exponential itself again, except we have this constant attached to it, okay? And so with this in mind, we create the antiderivative for the more general exponential, and we get itself again, but we have to account for that constant, right? And so when you take the derivative, this constant pops out, canceling with the one down there, so we get what we want. Okay, so these are our rules for taking antiderivatives of exponentials. We will certainly use the top one way more than the other one. So what's great about these rules is that we can also use them in conjunction with the rules we've developed previously. We don't have a huge toolbox yet, but substitution is one of the things we have, and we're going to use that a couple times here in conjunction with this rule. So for instance, let's do a couple of examples. Suppose I have the antiderivative of e to the x over 2. Okay, right? Let's be clear, what this rule says, we can't apply this rule here because this rule tells us precisely what it means. It means that if we have the exponential taken to the power of x, we have e to the x, the antiderivative is e to the x again with a constant. We don't have e to the x, we have e to the x over 2. It's similar but not the same. So we need to do something else here. And that something that will work here is we can use substitution. If I write that u, if I let u equal x over 2, so that du dx is 1/2, or I can rearrange this conveniently to write dx equals 2 du. With that substitution, I get e to the u times 2 du. I can use properties of multiplication. This multiplication commutes. And then properties of integrals tell me that I can slide that constant out front. And so now, this piece right here is precisely the rule, right? I've just happened to use a different letter, a different variable, but the relationship remains the same. The exponential of our independent variable, the antiderivative of an exponential to this independent variable is just that function itself with a constant of integration, and we might rewrite this as 2e to the u plus c. You might ask why I haven't written plus 2c and distributed that. We're pretty casual with constants. That c represents an arbitrary number. 2c is just an arbitrary number, and it doesn't really make it any clearer to have the 2 there, so we typically just write the constants on their own. And so now we can put back in the substitution that we started with to get the result that the antiderivative is equal to this. A good question, sorry, I'll say that next. Just want to point out again that we're using this new rule in conjunction with our old rules, and this is going to be this is something we do often in math, right? Where we start piling on the rules, and we need to get. We often have to go through several of them to arrive at our result. Let's also mention that we can check our work here. It's always good to know how to check your work in something. When we solve an algebraic equation, right? You have an equation with x in it, you solve for x and get a number. The way you check it is you put it back into the original equation. Does it actually make that original true? The way we check these is when we get our result, if we take its derivative, it should equal the function we started with, the integrand. In other words, if I take the derivative of 2e to the x over 2 plus c, do I get back what I started with? So I can take the derivative, distributes over addition. I can also slide that constant out front. If you haven't done derivatives in a while, this might be a nice little review. The derivative of a constant is just 0. So there's my 0. Here, I have to use the chain rule. The outer function is the exponential, which just gives us the same function back. But the chain rule says multiply by the inner function, the one we've composed, and that's x over 2. We just took that derivative right over here. It gave us a derivative of 1/2, and that 1/2 and that 2 combine to give us a 1. And so we end up with just e to the x over 2, which is exactly what we thought, right? And you can also see in this the relationship between substitution and the chain rule. That's what usually substitution is. Substitution is unwrapping that chain rule for us. There was a chain rule here that's not clear when we wrote this this integral. Okay, let's do another example. Let's do another one with substitution. Here I've got x e to the negative x squared dx. Again, this is going to be a nice one to use substitution with. In this case, I'll try u is equal to negative x squared. We'll get du is equal to negative 2x dx. All right, maybe I'll do my substitution a little differently here. There are different ways to write out substitution. So if I notice I've already got an x dx in here. I need a negative 2. I can't just write negative 2 because I want to. What I can do, though, is write something like negative 1/2 times negative 2 x e to the negative x squared dx, right? Because all I've done here is add a factor of 1, which doesn't change anything. So now I see that I've got my negative 2x dx. That can be replaced by du. I've still got a negative 1/2. I'm going to go ahead and slide that out front. And this e to the negative x squared will become e to the u. And there's my exponential again. And I get negative 1/2 e to the u plus c. And then I have to put the original substitution back in. So u becomes negative x squared, and there's my plus c. Okay, and I'll leave that one to you to check, but again, you'll see a chain rule that you have to deal with there to get back to the original function, the integram that we started with. Okay, all right, that is it for exponentials. Let's look now at the inverse function to exponentials. Let's look at the natural log. You can make a rule for other bases, but this is the most common, so let's just do that one in this. So let's come up with another rule. Let me give myself a little space here. So we're going to now take the derivative of the natural log of the absolute value of x. So we don't usually think about taking derivative with the absolute value, but I'm doing that because it's a more general function than without the absolute value. Our domain here is all the numbers except for 0, as opposed to just all the positive numbers. And the reason we need to do this, well, let's take this derivative. When we take this derivative, we get 1 over x. And so I'm thinking ahead to we're going to be going backwards. When we get 1 over x, we don't know whether or not it came from the natural log with an absolute value or not, because without it, it's also 1 over x. And so this covers all of our bases. So we use this rule to make this rule about derivatives to make a rule about antiderivatives. If we have the antiderivative of 1 over x, then our antiderivative is the natural log of the absolute value of x plus our constant. Note, just remember your rules of exponents, this is the same thing, right? Plus c, right? X to the negative 1 is just 1 over x. We sometimes forget that. All right. So this is another rule we now have in our toolbox that, again, we will end up using with other rules. So for instance, right, we might be tempted to write something like the natural log of the absolute value of 3x. It feels a lot like we're just applying this rule. It's got natural log there. We have the 1 over something here, and we get the natural log of that something. But this is not correct. Let's see why. Let's take the derivative of the natural log of 3x. Well, the derivative of the natural log, this is going to be a chain rule. We're going to get 1 over the thing inside, which now feels like it's pretty good, except we've got a chain rule. We have to multiply by the derivative of 3x, right? We've composed the function 3x with the natural log of x. And so these the derivative is not 3x, the derivative is just 3. And so the 3's cancel, and we get 1 over x, which is not what we started with. And so this can't be true, okay? So let's see how we can solve this. We need to start by recognizing that 1 over 3x is not the same as 1 over x, so we can't apply this rule. But what we can do is a little bit of algebra. If we remember our rules of fractions, this is the same as 1 over 3x, and then constant factors can slip out front of our antiderivatives, right? If you've got a function times a constant, you can bring the constant out front. And so now we can apply that rule, because now we precisely have the antiderivative of 1 over x here, right? And so we know what that symbol is equivalent to. It's equivalent to the natural log of x plus c. And again, I can distribute this, but I just let the 1/3 be absorbed by the constant since it's arbitrary anyways. And there is our result, right? And so when we applied the rule naively without recognizing that it's not quite the same. We didn't get the right thing, right? Our work up here was incorrect, but now we've got something that will give us, that is the right antiderivative, okay? All right, let's do one more. Let's do a complicated one for fun. So this one's got quite a few pieces in it. So this is an ugly looking function. And while this one was invented to kind of work out perfectly, this kind of stuff does show up, right? Things get complicated out there in the universe. And so sometimes we have to be able to sift through some of the nonsense. All right, there's our integral. We've got 1 over x times the natural log of x times the natural log of the natural log of x. Right? It's very reasonable to look at this thing. I didn't like how that one wasn't centered. It's very reasonable to look at this thing and not really have an idea where to start. And when that happens, you just start with something. You just try some things. There's nothing wrong with trying something and finding out it doesn't work. So I'm going to try a substitution, all right? And there's lots of things we can try. I'm going to try something simple. So let's go ahead and do u is equal to the natural log of x. Du is equal to 1 over x dx, okay? So let me rewrite this integral. I'm just going to rearrange some of the things in the denominator. I've got 1 over natural log of x, natural log of the natural log of x, and I've got 1 over x dx, right? So notice all I did was peel off that 1 over x. This is still the same thing. I just want to make it clear that we've got our 1 over x dx sitting there. And so now I can make all those substitutions. Let's use some colors. I don't know if this helps. Maybe it helps. We'll get u, natural log of x is equal to u. And then we've got the natural log of the natural log of x, which we're now writing as u. And then the 1 over x dx becomes the du, okay? So I've replaced everything I can with that substitution, okay? I've still got an ugly integral, right? I don't have 1 over u, I've got this other thing with it. Well, we can substitute again. So let's now try v is equal to the natural log of u. And then dv is equal to 1 over u du. So let's see what happens with our integral now. Let me rewrite it again as I did a minute ago. I can rewrite this as 1 over the natural log of u times 1 over u du. And so now, when I replace everything, the natural log of u is now replaced with v, and 1 over u du is replaced with dv. Now we have precisely the form we need to write this as, to use our antiderivative rule. The antiderivative of 1 over v is the natural log of the absolute value of v plus c. And now we just have to go back through our substitutions. The natural log of v becomes absolute value of v, becomes, the v becomes the natural log of u. And then the u becomes the natural log of the natural log of x, right? U becomes natural log of x. And we get this ugly looking function. And that's our antiderivative, right? Again, you can take the derivative, it'll have a couple of chain rules happening, and you'll end up with what we started with in the integrand up here. All right, so these are just some nice rules to have in our tool belt. The natural log and the exponential are functions that show up all over the place, so we need to be able to deal with them. And then we need to be able to mix that rule with the rules we already have. We're still early on. We're going to be gathering more and more techniques for integration. So we want to really get these ones solid before we start adding on here. Okay, that's it for this one. Thanks, everybody. I will see you next time.